Everyone, in this video, I'm going to talk about what I did in homework 4 and the basic concept behind it. The objectives for this homework are to perform AR tracking and 3D reconstruction of an object. You can see below 2 videos of the results. To perform an AR tracking, the first thing we have to do is to calibrate our camera because different cameras has different resolutions and different lens characteristics. In this step, we can get a camera intrinsic metric. And then we will also have to know the camera pose related to the image. We have to find the features that can be repeatedly found in multiple images. We can match the feature that appear on both images and then perform the pose estimation to know the rotation and the translation metric. The features here I use are grid features. Once we complete the step 1 and step 2, we know the intrinsic, rotation, and the translation metric. We can project anything onto the image to augment it. The right picture is the checkerboard I used to calibrate the camera, and the left video is the result that I render an AR object using the pose. Now, let's talk about a more difficult problem, 3D reconstruction. The goal here is to reconstruct the image by the point cloud. First, we have to calibrate the camera and use the features to compute camera pose. However, to get the depth of the object, we also have to use the image taken from different angles to compute the depth of common features. Therefore, we also have to compute the relative pose between cameras. Below is the image showing the matching features between two images. You can see the matching is not really good, so we have to add some constraints to improve the quality of the matching. The first thing is to use the epipolar constraints. When two cameras view a 3D scene from two different positions, there are a number of geometry relations that lead to the constraint between the image points. Therefore, we can use it to remove some bad features. Also, I remove the feature that only appear a few times, further refining the feature I use. Below are the results after I apply these two constraints. Finally, we can compute the depth of features. Here we have to build an M metric using the coordinates of these common features. And the target is to get the optimal lambda that minimize M lambda. Here is my result. You can see the red point at the bottom that represent the marker, and the blue point behind are the point clouds of the red box. Thank you for listening.